let's see how we can fix the problem with the previous implementation. If the problem is that all of the CPUs are repeatedly spinning on the atomic operation, let's try to separate the test part, which is checking the value of the log, from the atomic. The intuition is that for the testing, we can potentially use our caches and test the cached copy of the log, and only if the cached copy of the log is indicating that the log has changed its value, that it's free, only then do we try to actually execute the atomic operation. So here is what the resulting Spinlock lock operation will look like. The first part checks if the log is busy. This checking is performed in the cached value. So this is the not involving any atomic operation. We're just checking whether a particular memory address is set to 1 or 0, so it's busy or free. On a system with caches, this will clearly hit the cache. As long as the log is busy, we will stay in this while loop. We will not evaluate the second part of this predicate. So if the log is busy, this is 1, this is true, the entire predicate is true, so we will go back in the while loop. What that also means is that as long as the log is busy, as long as this part is true, the test and set, so the atomic operation, will not be evaluated at all. We will not attempt to execute it. Now, only when the log becomes free, so when this part of the predicate log equals busy, when this is not true, only then do we try to evaluate the second part of this predicate. At that point, the test and set operation, the atomic instruction, will be executed, or will be attempted at least, and then we will see what happens, whether we acquire the log or not. So what this also means is we will try to make a memory reference, since the test and set performs a memory reference, only when the log becomes free. This spin lock is referred to as the test and set spin lock. It is also referenced as a spin on read spin lock, since we're spinning on the read value that's in cache, or spin on the cached value, so because this is the behavior of the log. The Anderson paper uses the spin on read term to refer to this lock. From a latency and delay standpoint, this lock is okay. It's slightly worse than the test and set lock because we have to perform this extra check whether the lock is busy or not that hits the cache. But in principle, it's good. But if we start thinking whether or not we really solve the contention problem by allowing to spin on the cache, we realize that this is not quite the case. First, if we don't have a cache-coherent architecture, then every single memory reference will go to memory, just like with test and set, so there's no difference whatsoever. If we have cache coherence with write-update, then it's not too bad. The one problem is that all of the processors with write-update will see that the log becomes freed, so regarding the delay, and so every single one of them will at the same time try to execute the test and set operation, so that can potentially be an issue. Now, the worst situation of using this particular Spinlock implementation is when we have a write-invalidate based architecture. In this case, every single attempt to acquire the log, not only that it will generate contention for the memory module, but it will also create invalidation traffic. Now, when we talked about the atomics, we said that one outcome of executing an atomic instruction is that we will trigger the cache coherence, so the write update or write invalidate traffic, regardless of what the situation is. If we have a write update situation, that coherence traffic will update the value of the other caches with the new value of the log. If the log was busy before the write update event, and if the log remains busy after the write update event, great, no change whatsoever. That particular CPU can continue spinning on the cached copy. However, with write invalidate, we will simply invalidate the cached copy. So it is possible that the log was busy before the cache coherence event, before somebody executed an atomic instruction, and if the atomic instruction was not successful, we're basically continuing to have a situation in which the log is busy. However, as far as the caches in the system are concerned, that atomic instruction just invalidated their cached copy of the log. The outcome of that is they will have to go out to memory in order to fetch this copy of log that they want to be spinning on. So they will not be able to just spin on the cached copy. They will have to go ahead and fetch this log value from memory every single time somebody attempts to perform an atomic instruction. So this type of behavior will simply just compound the contention effects and will make performance worse. The reason basically for the poor performance of this lock is that at the same time, everybody will see that the lock has changed its state so that it has been freed, and everyone will also at the same time try to acquire this lock.